Hi guys, welcome back to another video. And I know I've been uploading roughly after 1 year. I had been terribly busy with my college studies, so I could not take out the time to make videos for my YouTube channel. But anyways, the video today is going to be very interesting. Today we're going to be understanding how do computers generate random numbers and how to specifically break Java's java.util.Random random number generator using C++ and something which is called as modular arithmetic. So first of all, we're going to be doing a little bit of theory about how do computers generate random numbers. So I actually have this little slide made over here. So basically, computers do not actually generate random numbers. They generate something which is called as a pseudo-random number, which is done by a PRNG algorithm, a pseudo-random number generation algorithms. So there are two categories of PRNG: cryptographically secure and non-cryptographically secure PRNG. And the most used in programming languages are non-cryptographically secure PRNG, which are of three categories: LCG, XOR shift, and LFSR. LCG stands for linear congruential generator, and LFSR stands for linear feedback shift register. And the main focus of this video is going to be LCG. I'm not going to be focusing much on XOR shift or LFSR. You can watch videos about this on Computer Files YouTube channel. He has done a great job explaining this. But the main focus of this video is going to be LCG. So LCG stands for linear congruential generation algorithm, and it's a very simple algorithm which is defined mathematically as this: xn plus, this is a screenshot from the Wikipedia page. So xn plus 1 is equal to axn plus c mod m. So xn is the seed value and xn plus 1 is the next random number which is generated, and a, c and m are the constant. M is called as the modulus constant, A is the multiplier, and C is the increment value. So the java.util.Random algorithm under the hood uses LCG. So actually, if I go to the Wikipedia page of LCG over here, you can read it if you want to. It's pretty interesting. There are certain predefined values which are taken by Java, the predefined constants. This entire table, parameters in common use, you can go through it. We have the values for Java, we have the values for C++ also, C++ rand function. C++ rand function, I believe, uses XOR shift, so the values for there would be in the Wikipedia page for the XOR shift. But over here you can find java.util.Random, and the multiplier used over here is 2 to the power of 48. I can just go back over here. So the multiplier is 2 to the power of 48. The modulus is 2 to the power of 48, sorry. The multiplier is this big random number. The increment value is 11, and we don't care about this. And there are certain values which are normally taken when you define your own LCG implementation. So over here you can see the period length. So there are three common families of parameter choice. So m could be a prime and c is 0. M is a power of 2 and c is 0, and m is a power of 2 and c is not 0. So this is basically the variations which people or engineers commonly use when they are implementing these algorithms. You would see in the table itself these modulus values are quite repeated, like 2 to the power of 31, 32, 63, 64. And even the increment value and the multiplier values, these are generally repeated because they are mathematically said to be stable and give a very large period of values before the numbers start repeating. So the values for Java's constant are such, and you can find the source code of java.util.Random on OpenJDK. So basically I have the screenshot over here. You can even go there. This is the link. So you can just do a quick Google search, GitHub OpenJDK, and go to the following link and open random.java. And over here, I actually have the screenshot over here. So you can see the multiplier has this value, the addend or the a value, not the a value, actually the c value over here. We have defined the incrementer as c. So the addend is the incrementer. So the c value over here is this is hexadecimal. So 0xbl, the L over here denotes long, and 0x denotes hexadecimal. So when you convert the remaining b to hex from hexadecimal to decimal, it converts to 11. So the addend over here is 11, which aligns with what we had mentioned over here. So these are the values which are defined for our multiplier, and addend and mask. Mask is basically the modulus value. And actually I would like to open it over here because we need to copy these values. So I would just search for multiplier and just go up over here. Yes. So the way we're going to be doing or implementing this is, first of all, I'm going to be writing a random number generator in Java, and then we're going to be breaking it. So the first thing which we do is, it's been a while since I've written code in Java. In college, I'm mainly focused on C++, C, and Python, and for my personal project, C++, assembly, and low-level stuff. So it's been like roughly 4-5 years since I've, not 4-5 years, 2-3 years since I've written Java. But anyway, so I believe the way we write is first of all, we have a class main, and I read this code somewhere that everything in Java is an object. So that's why Java is like the perfect example of an object-oriented programming language. So the first thing which we do is define the class. So we call the class main, and let's just do it like this. And we need to import a couple of things first. So what we do is we do import java.util.Random, because we're going to be using the random number algorithm. Then we're going to be importing the scanner class also. It's not relevant to our program, but it would be relevant to basically display the numbers one by one by taking the enter input or pause input. Basically, you'll understand this when we implement the code basically. So we import the scanner package, and then we define the public static void main. So public static void main, and string, we don't need the string args actually, so we'll just skip that totally. And then over here we're going to be defining the scanner object and the random object. So scanner sc is equal to new scanner, your basic Java code, and we're going to be taking the input from system.in, and then the random object rand is equal to new random, and then we're going to be just generating random numbers. So let's generate a random number from counter 1, and while 1 is less than 2. So this loop would run infinite times. What we do is we just do int new value, or the new random number, is equal to rand dot next int. This is the way we generate random numbers using the java.util.Random algorithm, and then we display it basically. And we just do counter plus plus plus, we add a little bracket over here, and then we add the new value which is being generated. And the reason I incorporated the scanner packet is basically I wanted to do this sc.next line, so that we would have to press enter, and then is when we'll get the next value. So the infinite loop wouldn't just bombard us continuously with new random values. So let's run this. And okay, we have an error over here. So I'll just call this public. Maybe we have to make it public. It's been a while since I've written Java code, so you can't blame me actually. So maybe I'll have to use string args over here. I'll just run it again, and it works now. Okay, so now we have the random numbers generated. So first is this random number, then we have this, then we have this, so on and so forth. So what we're going to be doing is we're going to be using C++, and we're going to be understanding how this algorithm works in depth, and then we're going to be through reverse engineering, we're going to be breaking the algorithm, and then we're going to be predicting the values which will be generated by this algorithm. So first of all, I'll create a new C++ file. So I'll just call it code lcg.cpp. Now I'll just write the boilerplate code. IOStream and int main, int argc, char double pointer, argv, and then we just return 0. So let's just run this. And yeah, it's working fine. So the way this algorithm, the way java.util.Random works is basically the seed value. Okay, I have to go back over here actually. So this is basically the standard layout of an LCG function, is that an xn plus 1, which is the next random number, is equal to a into xn plus c mod m. So A, C, and M, these three are the constant values, and xn is the seed value of the previous random number through which we use the constants, we apply the constants values on and generate the next random number. So it's pretty simple, but a little bit of a caveat over here is that Java uses a 42-bit, a 48-bit seed value for xn and xn plus 1. So the seed value or the x value is of 48 bits, and the value which we receive on the new value, which is the integer value, is 32 bits, because 8 into 4 is 32. So we have a 32-bit value over here, whereas the seed value is 48. So what exactly is happening over here is, if I just go back over here, the seed value is 48 bits, whereas the rand int returns a random integer, and an integer, the size of an integer is 32 bits. So how do we convert this 42-bit value to 32-bit? So of course we are running the algorithm, that's for sure. So for an example, when we have a seed value, whatever the seed value is, we apply the constants on it, so a into xn plus c mod m, and we get the xn plus 1 value, which would be the new random number. But how do we convert the 48-bit random number to a 32-bit random number? So basically what we do is we remove the lower 16 bits. So 48 minus 32 is equal to 16. So what we do is we remove the lower 16 bits. So for an example, if we have xn plus 1, let's say, what we do is we right shift this by 16. So we remove the 16 bit, and then we typecast this to an integer of 32-bit. That's how you typecast in C++, sorry. So we typecast this to the following type, and we shift it 16 times. So when you shift the 48-bit value 16 times to the right, the lowest 16 bits are removed, and hence we get the remaining 32 bits, which are the value of random int, which is returned by the LCG. So with this in mind, we can understand and start implementing the code. So first what we have to do is basically we need to define the constants over here. So we have three constants, a, c, and m, and if we go to OpenJDK, which should be over here, we can get the value of them. So what we do is we define them right over here. So I can just define them outside, so we can just do constant. So now we need to define what our constant values would be. So we have three constants over here, as you can see. The value of a, c, and m are constant, and we can get the values of these three from OpenJDK's source code. So what we do is basically const, we can define them as a const unsigned integer of 64-bit and underscore t. I don't know why autocomplete isn't working over here. And then we call it a, and the value of a would be equal to this. So when you copy this and paste this, actually you can do it directly, or you can convert this entire hexadecimal into its corresponding decimal. So you paste this over here into a hex to decimal converter, and the last L value is actually denoting that this is a long value, and you can just remove this, and when you convert this, we get the following number, which is the decimal representation of our a value. So we just copy it and paste it over here. So we have our a value. Now we need a const u int 64t, and then we need the c value. The c value would be, I'll just run this again. 1 second. Let's just do this, and it's pretty annoying. So I think we should be getting, yeah. 64 underscore t. It's very annoying to type it again and again. So we have the add-in value, which is hexadecimal b. So you can just do it like this, or the value of this is 11 anyway, so you can check it over here also. So we just copy this, and we call this c and 11, and then the final value would be the modulus value. So u int 64 t m, and the value of that would be 2 to the power of 48 minus 1. So one thing you could be confused about is over here the value of modulus is 2 to the power of 48, but actually the value of modulus over here is 2 to the power of 48 minus 1. Why are we doing this? So one thing you need to understand is basically, I'll just mention it in a comment over here. Let's do a multi-line comment. So the formula of LCG is basically xn plus 1 is equal to a times xn plus c modulus m. That's the formula of LCG. So I'll just put the brackets over here also, so it's more clear. So over here we're using the modulus operator, but another way of achieving the same thing is xn plus 1 is equal to a times xn plus c, and we do a bit mask with and we put the mask over here, or the m value over here. So this is much quicker because we are using bitwise operator, and the way we're going to be cracking the seed value or the algorithm is we're going to be brute forcing it to a range of 2 to the power of 16. You're going to be understanding this further when we write the code, but if we do it in this manner, it's going to be very long. Because comparatively bitwise operator is much more faster. So to do it in the following manner, by using a bitwise AND operator, we need to subtract 1 from the m value. So the m value is 1 to the power of 48. Sorry, 2 to the power of 48. I believe you know this means 2 to the power of 48. And then we subtract 1 from it. And to not get any weird errors about with overflow, we just make it an unsigned long. So this is the reason we are doing this. So now I believe we have all of our 3 constants ready, and I think we can just run this. Nothing's going to happen, just run this and check. Yeah. So now what we're going to be doing is we have to understand how are we actually going to break the code. So what we need to break the code is we would need 2 consecutive outputs from the random numbers. So whether it be 1 or 2 or 2 or 3 or 4 or 5, whatever. So what we need is we are going to be needing the 2 consecutive values, and once we have the 2 consecutive values, we would be ready to break it. And the reason we would need 2 consecutive values is because of the thing which I explained over here. The seed value is 48 bits, but if we have just one value, we would be short of 16 bits. And then we would also not be able to predict the values because we don't have the lower 16 bits. So because whenever we run randint, it removes the lower 16 bit and then it gives us the value. So to get the value, we would need 2 consecutive values, xn and xn plus 1, and through that we're going to be brute forcing it, and then we'll receive the lower 16 bits, and then we'll formulate the entire seed. So what we need is the first 2 consecutive values. So I'm going to be doing it on the command prompt or the command line itself. So as I said, the value or the output of the random number is a 32-bit integer. So int 32 underscore t is equal to output 1, and we're going to be receiving this from the command line. So argv and 1. argv0 is the name of the program, so argv1, and we need to convert it to an integer. So we do std string to integer, and we pass argv to it, and we do the same for int 32 underscore t output 2 is equal to std string to integer argv and then 2. So now we have both of these values ready. So now what we're going to be doing is we need to find the lower 16. I'm just going to write it over here also. We need to find the lower 16 bits. So we need to brute force the lower 16 bits, and we need to check whether it fits with our predicted value or not. So what we're going to be doing is we're going to be running a for loop. So for int lower bits is equal to 0, lower bits is less than 2 to the power of 48. So that would be 1 shifted for 16 times. I'm sorry, it's not going to be 48, it's going to be 16, because we need to find the lower 16 bits. So we run a loop of lower bits from 0 to 2 to the power of 16, and then we're going to be incrementing it with every iteration. So now inside the loop, we are going to be first defining our xn value. So I'm going to be roughly writing the code first in the comments. So xn would be equal to the output 1, and we're going to be shifting the, so basically what we're going to be doing is we have the output 1, and through the output 1 we're going to be predicting the lower 16 bits of the output 1, which aligns with the output 2. So output 1 over here would be our xn, and output 2 would be xn plus 1. But the thing over here is, since we only have the 32 bits, we have the missing 16 bits. What we're going to be doing is we're going to be brute forcing or iterating over the lower 16 bits, and every time we brute force, what we're going to be doing is we're going to be shifting output 1 to the left 16 times so as to accommodate space for the lower 16 bits, and then we're going to be bit masking an OR and putting over the lower bits. So basically what this would do is we have the 32-bit output 1 over here, which acts as our xn, which actually is not our xn, because xn is supposed to be 42 bits, 48 bits, whereas this is 32. So to add the extra lower 16 bits, basically what we do is we first create the space for it to accommodate it. So we shift it left 16 times, and after that we just OR it with the lower bits, which is over here. So to do it in a programmatical way, what we do is we have an unsigned integer of 64 bits. This is supposed to be 48 bits, but we don't have a specific 48-bit variable in C++, so we can just use 64-bit. It would serve our purpose. The upper remaining bits would be 0. So a 64-bit unsigned integer, we'll call it xn, would be equal to, we take the output, we shift it 16 times, and then we OR it with the lower bits. So we do a bit mask OR with the lower bits. Now what we're going to be doing is output 1, So now what we're going to be doing is we have to typecast this twice. The reason for this is because the output 1 can be a negative value also, and when we shift the negative value without accommodating for it in an unsigned manner, what happens is it would give us some unsigned error, and it just gets a bit messier. So what we're going to be doing is we're going to be typecasting it first to an unsigned integer of 32 bits, because this was before you would see it was an signed integer. So we convert it first to an unsigned integer, and then finally, after we have converted this to an unsigned integer, what we're going to be doing is we're going to be converting this to an unsigned 64-bit integer. So I'm going to be explaining this again very shortly. We need to accommodate the space for the lower bit, so we shift this left 16 times, and then we bit mask and OR with it with the lower bit. So now we have our seed value ready. But before shifting it right, if the value is negative, it would be a bit messier. The values would overflow. So to avoid that, to deal with the negative value, we typecast this into an unsigned integer of 32 bits, and then finally to receive the actual value, which aligns with what we had declared it over here. The actual seed value is supposed to be an unsigned integer 64-bit or 48 bits. So we convert this as such. So now we have our proposed xn over here. So what we're going to be doing is we're going to be finding the xn plus 1 through the formula of LCG, which we had mentioned. So the formula of LCG is a into xn plus c is equal to mod m is equal to xn plus 1. So what we're going to be doing is unsigned integer 64-bit xn plus 1 is equal to this. We're going to be copy pasting the formula. So a into xn plus c, and instead of mod m, we're going to be using a bitwise operator, bitwise and m. Hence the value of m over here is -1, because we're going to be using bitwise and. I explained this before also. So we have our xn plus 1 over here, and now the xn plus 1 would be used to extract the output 2 basically. I said before that what we do is basically the randint returns a random integer of 32-bit, but our xn plus 1, even though we have declared it to be a 64-bit, is actually a 48-bit seed value. So we're going to be removing the lower 16 bits to get the next prediction. So unsigned integer 32-bit, we'll just call it next prediction, and we remove the lower 16 bits the same way which we had done over here. So what we're going to be doing is we just do xn underscore 1, and then we remove the lower 16 bits by shifting it right 16 times, and then we need to typecast, this has to be capital N, and then we need to typecast it into the proper type. So int 32. You can use an int over here. You can use you don't need to use a uint over here, because this was defined as an int over here, and we're going to be comparing this and this. So it makes more sense for both of them to be of signed type. So now we have the next prediction. So what we're going to be doing is we just have to make sure that if the next prediction is equal to the output 2, then we have found the correct seed value or the correct lower bits value, and then we can generate the next string of random numbers. So basically we can just do a std cout seed value found, and we can just do x, we can print xn, and then we can just print out the next string of random numbers. So let's print out the next 100 random numbers. So we can just run a loop, I is equal to 0, I is less than 100, I plus, and then what we do is basically we need to define the xn every time. We need to update the xn every time. So xn would be equal to a times xn, the normal LCG formula. And we need to first we add the accumulator or the C value, and then we bitmask it with the M value. And then the reason we're not using xn plus 1 over here is because once we have used this, we don't need to. You can actually even do this like xn1, and then ultimately after we have displayed the number, you can do xn is equal to xn1. You can do this also, but there's no need of doing that, because ultimately once we have used this, there is no need of the previous xn value, so you can update it right away. So once we have updated that, we need to print the value. So, before that, we need to extract the lower 16 bits. We need to remove the lower 16 bits to get the required random number value. So what we do is we call it int 32 random number, or the predicted random number. That's going to be the xn value, and we just remove the lower 16 bits. That's it. And then we can just print out the value. So we can just do I plus 1 and add a little bracket over here, and then our predicted random number, and then a new line. So I think the program is done. I don't think I'm missing anything out over here. Let's just run this and see what happens. So of course I haven't given the value over here, so we need to provide the value. So over here, let's run this again. So for an example, we have the first random number is this -21197 blah blah blah. So we just copy it and we paste it as our first output, and then the next random number is 5268, and we just copy it and paste it as our output 2. So once we enter it, it takes a little time, but it finds the seed value using the lower 16 bits, and then it predicts the next string of random numbers which would be predicted. So we can do a one-to-one comparison and find out whether it's true or not. So over here you would see that we have 5268196, 526809196, 526809196, and the next random number which is predicted by our model is -131446970. So when I press enter, it's -131446970, and you can see it continues on forever, like the value is predicted forever. So all the values are predicted. So this was it for the video, and the reason I made this is it's pretty interesting because there are a lot of security concerns with this video also. There used to be I think it's still active, I'm not really sure, but there used to be a Java framework for backend servers called Jetty, and Jetty basically handed out session tokens based upon random numbers. So I think this there is this very famous book, the Web Applications Hacker Handbook. I believe some of you would have read that, and this was mentioned over there. So Jetty used to hand out random numbers or the session tokens basically as random numbers through the LCG output, and there was a PHP developer who found out the source code of Jetty, and he noticed that the session tokens, which when someone logged in, the session token was, which seemed to be random, was actually pseudo-random and was handed out by LCG algorithm by using java.util.Random. So he broke the LCG code in the following manner, which we did in this video, and then he could predict or log in as anyone by predicting the session token. So that was a pretty big flaw, and people normally don't use this for security purposes. For security purposes, you would use a cryptographically secure random number generator, like a Mersenne twister. I believe that's a cryptographically secure random number generator. Or you would use something like, I believe, NVIDIA or Cloudflare. I think Cloudflare. Cloudflare uses a lava lamp. Basically, they have a set of 50 lava lamps, and they use the photo of it to put it back through their servers, and they use the entropy of the lava lamp to basically generate truly random numbers. So people go to a lot of lengths to generate random numbers. But anyways, so this was basically how to break Java's Java's random algorithm. And the other random algorithm which I mentioned over here, XOR, shift, and LFSR, they can also be broken through the following mechanism. It's pretty easy. It's basic mathematics, and if you know coding, it's very easy to break them. So that's for the video, guys. Thank you for watching, and bye bye.